All right, guys, so here we go. So the next lecture is going to be the PVA relationship, PVA standing for position, velocity, acceleration, and how we can graphically maneuver between the three concepts. Eventually, we'll add some force to it, but we're going to stick with the PVA at this point in our discussion. So the purpose is to understand the relationship between the three. In the task, we'll review some of the terms. We'll look at a little bit of a quantitative approach. Then we'll do more of the qualitative approach, which is going to be what we're really going to be using for this lecture. Um, and then what we'll do is look at some applications. And the application piece is really what we're going to spend time on in lab this week, as well as some lecture on Wednesday. All right, guys, so here we go. We're going to talk about the terms that you need to know and how they relate to each other. And so the PVA, if I ever ask you what PVA, just tell me what those terms stand for: position, velocity, acceleration. But I want to make sure we're clear on what they are and what derivatives each one is to the other. So position, I have it as P, D, or S, depending on what textbook you look at. It could be referring to any one of them. But it's particularly just where in location of space you are. But it's very important that you look and we talk about this concept of reference point, because the reference point is where we talk about our origin, and that dictates what everything is with respects to where we start and where our positive and negative position occurs. So whenever you set anything up, you always got to make sure that you set up your reference point, typically starting with your origins of 0, so you can pick your 4 quadrants, positive and negative. This is direction dependent, where that origin comes into play, and it's very specific and important. And then you can have many units of measurements of length throughout this process. Now, the derivative position, or the rate change of position, is velocity, and that it will always be a lowercase v as representations. And again, remember, this is direction dependent. So if your position slope is positive, then your velocity should be in the positive form of your graph. And if it's negative slope of the position, or the negative derivative of position, you should be in the negative portion of the velocity. And we'll show you a little bit what that means in a minute. But again, the measurement is some kind of length per time, meters per second, miles per hour, feet per minute, those type of concepts. And then we have the derivative of velocity, or the rate change of velocity, is acceleration, typically referenced by a lowercase a. And this is direction independent, meaning it doesn't go back up to the reference point, so it doesn't have any reference with this. It is more to do with the slope and rate of change of this guy, velocity. Okay, so that is what we're going to be dealing with there. And then the velocity of unit per time. So it's whatever your velocity units are per another unit of that time, whether it's seconds squared or hours squared or minutes squared, it's in reference to your velocity. And so what is the derivative? Well, the derivative is simply taking the slope of the line, right? So it's the rise over the run, the change in x, y over change in x. And it talks about the steepness of the line, so how that changes. And then what slope are we talking about? We're talking about the tangent. So thinking about what we talked in class about the difference between the average and instantaneous, we are taking the instantaneous slope at each point along the graph, because this tells us how at each time component of that graph the slope is occurring. So we make that delta x, the delta t, as small as possible, and we get it to where the tangent is only touching the line of the slope in one point, and that's the slope. So again, we have two terms to know: derivative and integral. So derivative is when we go from PV to A, and it's basically you take the slope or rate at which something changes. And then to integrate and go from A to V to P, you combine the infinitesimal data. So it's the area under the curve. So you create a bunch of rectangles because you're making your delta t so small, and then you summate them together, and that'll give you where you're going to go. Now, I will tell you that for this class, I only need you to know that you're going to integrate going the other way. I'm not really going to make you go from A to B to P. I just need you to know that if I go the other way, I'm taking the integral, and it's the area under the curve to go the other way. So that is all you need to know for integrate. And just know the derivative is what you're going to be dealing mostly because I want you to see the relationship from P to V to A. So here's how we work it. You have position, you go to velocity, and then we have acceleration. To go this way, you look at the slope of the line or the tangential slope, and that's the derivative. Now if I go acceleration to velocity to position, I'm taking the area under the curve and we're going to integrate. So this is a little schematic to show you how we go the process and what the relationship is from P to V to A. Again, just some more review. Slope equals rise over run, and that is delta y, or whatever your position, velocity, acceleration is, so whatever your y-axis represents, over your delta x. And in our case, the delta x is always going to really be time for this relationship. And there you go, rate of change. So that is what you are taking the derivative of. Now, to make this graphical representation, the theoretical representation, the qualitative representation of the PVA relationship, we're going to look at some critical rules that should make things a little easier for you. And if you follow these rules and follow the procedures that I outlined, you guys should have no challenge moving from PV into A. The hardest part then would be just establishing what your position graph looks like. But so here we have what these look like. IP is inflection point, min max, and then zero. So what happens is the inflection point, I'll talk to you about what those are, becomes a min max in the derivative graph. A min max becomes a derivative into a zero for the next graph. So these are essentially, you're following the slopes. So an inflection point is where the slope of the line changes direction. So as it gets steeper and steeper and steeper, it starts to get shallow. So it's a maximum or minimum steepness in that inflection. We call it concave up or concave down. And the min-max is whenever something's at a min or a max, the slope of that line, the tangent slope, is zero. That's why it becomes a zero in the next graph. So here you have a little bit more. So an inflection point is a change in slope. So if I have a slope that looks like this, and another one that looks like this, and another part, at some part in here, there's a shift in the slope, and we call that the inflection point. Okay, so it's where the concave up and concave down. Now, if I had continuous, we would put our slope, our inflection point, somewhere around in here. We call that the inflection point. And it's simply where you start getting steeper, 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 and then all of a sudden, at some point, you change and you're become more shallow in the process. And the tangent is the greatest in that phase. Now the min-max, now think of this as a local min-max. You can have multiple min-maxes along a curve or along an activity. And what you're going to see is we're going to chunk this up into little spots because that's what you have to do. And so it's the slope of the tangent is zero, and then there's no rate of change. So this whole slide right here is going to be very important for you to understand because this is going to describe to you how you move and transition from position to velocity to acceleration, going the derivative route. Okay, and keep in mind you only look at the slope of the line, the tangential slope of the line. All right, so now if you follow along in how we set the graphs, and it'll help you move along the process from the P to V to A. So follow this path, and it's going to make the quantitative or qualitative process and the theoretical process of this much easier. So you begin with setting up your graph. So you draw a long line, and that's because we're going to temporarily align all of the graphs. So as I come back up and I do my x-axis for each one, so you see how they're all connected, right? And then I just do a t here, and this is going to be seconds. So this is what I'm talking about where you label all your axes, right? So what typically happens is if I have graphs that go on top of each other and one is labeled on the x-axis, then that tells me that each of the axes going up are that way. But now I want you to label each one of these. So this is going to be position, meters, this will be velocity, and meters per second. And then down here, you have your acceleration, right? And that's meters per second squared. So when I ask you to label your axes and set it up, this is how you're going to set it up. So remember, the most important thing with this is everything is temporally aligned, and you'll see that come into play here in a second. What I mean by the origin, what does 0 here in the position mean? And what does it mean to go into the negative versus the positive of position? That's going to become very important as you go along the process, is understanding what puts me in the position positive and what puts me in the position negative. Whether my ground, or the ground is the origin at 0, or whether my starting position when I'm standing on a box is 0. That dictates if I ever go into the negative region of my position, which is very important going forward. And then as we go forward, what you're going to see is you begin with the known. So what information is given, the previous knowledge about a task, and then you separate it into sections. And what this means is, because you're going to set the position curve and that dictates the velocity and acceleration curve, you have to know what you're given. Whether I'm at free fall, that means that I know that if I go to the acceleration curve, it's a negative 9.8 meters per second squared. If I'm in the metric system, but I also know where my origin is, and that's a given, and then I know the direction where I'm moving. If I'm going away from the origin in the positive direction, I turn around and come back in the negative direction, what all that means relative to where the origin is. And then you should know some stuff about the task. And we all have our predispositions about tasks and what we know about it, but use that to your advantage in setting up these problems. And then I'll show you how to break up this into sections here in a second with the use of vertical lines. And this is part where you connect the critical events, the inflection points, the min maxes and the zeros in the 3 graphs that helps you transition down the line. So let's talk about what these look like. So this is actually quantitative data from one of my studies, and it's the center mass position. You can see the position on the left-hand side there in meters. You can see the time, and you see how those are individual segments on the x-axis with the sampling rate. This is a very traditional sinusoidal path along the process. And so what you're going to do now is, when you have this set up, and you notice this is all only in the positive, because where the center of mass is relative to the ground, which is the 0, or the origin in this case, it never really touches it, so it's always up. So what we do is, first we go through and identify with these x's. These are all the inflection points. So as you can see, it's kind of easy with the sinusoidal path where the concave down turns into the concave up, or where your steepest tangential slope is along the lines. Now the pink x's indicate ones that we know for sure. Now I will tell you, because if we just trace those out, because it's a sinusoidal path, we know that at those points of the x's, there's probably something happening on the outside there. Those are probably inflection points. That's why I put those there. But the pink x's are what we know for sure. The green, just because we know what this path looks like, we can assume that there is some there. And if we actually did the calculations, we would know that there are some there. These arrows are the tangential slopes equals 0. So again, those are min and maxes. The ones in the top in the dark in the blue represent the max, and the purple's the minimum. Now notice that there are 5 maxes and 4 minimums, and those are local max and local mins, right? So the one in the very center max would be if it was the max of the entire path, and then the third, moving from left to right, this guy right here would represent the minimum if it was just one minimum. But because we're doing min and max locals, then you have the process along the way, and there's multiple min and maxes. So this is how you go through and identify each thing. Now for your purposes, when I have you guys do this, what I want to see is not just here the arrow, but I want you to write it's a max, or I want you to write it's inflection point by IP. Because that to me knows that you not only have identified it, but what it is, and it'll help you move along to the next one. So you go through and you identify each one of these in the process, okay? Because that'll help you. Now I will tell you, if you notice I put these minimums here, what I would recommend you do is put it off to the side or up here, because of the next step we're going to do, and that's connecting the graphs along the process. All right, so now here we have the setup, right? So now we're gonna go through the entire process and how to connect them and go through it. So here you have the PVA relationship set up. Again, I have my time here. I've labeled my x-axis for all three: position, velocity, acceleration. Now, when you do this, I would always recommend doing position on the top with velocity and acceleration, the derivatives falling under line with that. So we're gonna take that same sinusoidal path that we started with before, but we're going to take a couple sections of it because I just want to point some stuff out to you and show you how to do it. So we're going to go ahead and identify our key critical events. These blue recommend the inflection points. Now, it's very important that because these are theoretical and we're not using data with them, the identification of these inflection points truly are a matter of how you draw your lines. And what that means is here I've drawn my inflection point on this one here. But if you put yours here, I'm not going to argue with you that it was correct or incorrect because it's just a visual representation of what we see, right? Because you can theoretically argue that this is more of a critical inflection point as opposed to that is along the process. So as long as you connect these down, like we're going to see in a second, I'm not going to argue with you whether you're right or wrong, okay? So those are the inflection points. Here we have the min and maxes. And again, it's a matter of how you draw it. Your min maxes may be a little more left, a little more right than I've drawn, but it's not any important. As long as you label them correctly and you move them from P to V to A correctly, then we're on the same path, okay? So these are those vertical lines that I talked about. So I've identified the critical events, the inflection points, as well as the min and maxes. And so then what I want you to do is, typically with a straight edge, I want you to connect the dots all the way down, and I draw them all the way down. And I literally do this every single time I do one of these because it makes it easier for me to transition. What is that transition like? Well, the inflection points and the min maxes become something in the next one. And if you look at this, remember we talked about this point right here is a maximum. So that becomes a 0 in the next graph. This inflection point here is a negative slope, right? And so we said that the inflection points become a min or a max in the next graph. So now that has become a minimum, right? So a minimum means it's a negative. A maximum means it's a positive, and that's what we have here on the velocity graph. Okay, so there's my negative. Again, the minimum becomes a 0. So if I draw this down, it became a 0. This inflection point, as opposed to the one preceding it, was a positive slope. So that becomes a positive. Now, what you'll notice is between this inflection point and this inflection point, I have them different magnitudes on this graph. So this one is a lesser magnitude. Let me change. So if I look at, let's call this inflection point 2, it's now a minimum 2, and this is inflection point of minimum 1. This is how you start to make your graph make sense. I don't know the magnitude of this one versus this one, but if I look at those two, the slope of my inflection point 1 negative is much steeper than 2. So you can do that theoretically when you do this process by making this one a larger negative magnitude-wise than that one. And that's how you make this transition along the line. Okay, now you'll notice that these two, my maximums, are pretty similar in magnitude. And that's because you really can't tell the difference between this one and this one. It looks like one might be a little flatter or less steep than 2, but I'm not going to sit there and nitpick that. So if you have this process, you'll be fine. Okay, and that's how you transition from one to the next. And then you simply connect the dots. Now, one very important thing that people forget to do, and I want to make sure that you guys don't do this, is notice that these graphs, because these rules have left off chunks of this graph. How do you figure out how to do that? Well, again, it always goes back to what happens in the previous graph. And you need to continue this. So if I see this, you're going to lose points because you didn't continue it off. And it simply looks like this. And how did I do that? Well, I know that this is a negative slope. And I know that it kind of starts off shallow and then it continually gets steeper until some point. And that's what I've drawn here. A steeper slope, magnitude gets bigger, and then it starts to mellow out, and that's what happens there. Here, it starts out, it's a positive slope, okay? but it starts out steeper, so there's a greater magnitude at the beginning, and then it gets smaller and smaller and smaller as it approaches the maximum. So you need to connect what happens at the end of your critical events, otherwise you lose points, okay? It's very important. So now what do we do? Well, now we're at the velocity, and the velocity curve looks like that. On the velocity curve, we're going to take and now identify the IP or inflection points as well as the min-maxes of that graph. So you'll see now the blues represent the IP again. So if I label these IP, this is a min, max, right? So we're going to go through again and label all those all the way through. So when I look at your graph, I'm going to look for those labels on these arrows and dots. Okay, so the dots are where you don't have to put the arrows. What I would want you to do is either put an X or your own dot representing where you want the ideas to be, where you want the inflection points, min and maxes. I've drawn the arrows because I just want to point them out more for you. Okay, so the idea now is we have these in the acceleration or the velocity graph. To go to the acceleration, the exact same thing we did before. We draw, this is a positive slope, so that becomes a maximum. This is a negative slope, so that becomes a minimum in the acceleration. And the mins and maxes in the velocity become these zeros. So again, you just have the same kind of concept, playing with the velocities or the magnitudes and where they belong of the acceleration. And again, you just connect the graph, connect the lines together, and then continue it out here based off the slope that you see and how that path is moving through the process. So that's how we connect them all the way down through P, V, and A. Okay. So now I want to give you a little idea of theoretically how to start and create your position graph. So if I tell you that I want somebody to do a squat and the origin is the ground, right? And we're going to follow the center of mass of the body through the squat. I'm going to give you 3 options for the position curve, and I want you to be able to think about which one it is, right? So remember, we're doing a squat. We're following the center of mass path over time, and this was 3 possibilities. It could be here, this one, or this one. So your options are A, B, or C, right? So let's think about what this means again. So on the axis here, we have time in second, and then if we go up here, this is position. Now, if I put this, I'll just put position meters, right? And so what we know is anything up here is positive and down here is negative. So remember, I told you that what I want you to do is look at the center of mass. The ground is the origin. So this right here is the ground I'm standing on. Okay, and anything on top is positive, anything below is negative. So we know because of that we can go ahead and cancel out A, because none of the whole entire movement is what this graph says A says. The entire movement happened in the negative relative to the origin, the ground. So that would be me doing the squat under the ground. We can also cancel out B, because at no point do I go through the ground. And that's what this portion of B says, is that I traveled underneath the ground at some point with my center of mass, and that's not the case. This would happen if I went into water, right? So if the ground under me had water and I fell into the water, I would go into the ground if I had the top of the water being the origin. So for our purposes, C represents what happened. I started with standing, I went down a particular height, but there was still some distance between my center of mass and the ground, and that's what that is, my center of mass height. And then I went back up to where I started from, my original height when I completed it. Now, if somehow I drew a line like this, right, that means my finishing height was greater than my initial height. So I probably would have had to step up on something, or I started in a semi-squat position, squatted down, and I went up to standing, right? So this is how we manipulate the position graph. We'll play around a lot with this, but start thinking about your task and what happens in the center of mass during your task. So in just summary, we have deriving graphs as a slope, and more importantly, the tangential slope, because that represents the smallest instantaneous concept with the slope at that particular line. When we go in the opposite direction from A to V to P, remember we're taking the area under the curve. Okay, so we're going to integrate those graphs. Here are our critical points. We call them those CPs. Inflection point leads to a min-max, which leads to a 0 in the following derivative curve. And always align your graphs temporally. That means on top of each other, right? Because this is going to help you along the line, okay? Because then we just draw the lines down and connect the critical points and have some fun with it. And that will determine how successful you are in this process. If you can follow all these, especially these points right here, the critical points, and aligning your graphs, you'll be successful at this. All you have to worry about is your position graph. And if you can set up a proper position graph and follow the critical points, you'll succeed. So you'll be happy to know there's no quiz for this one. We're going to spend some time in lab and lecture going over this material. Okay, guys, thanks a lot. Appreciate it.